guys. So I have some good news. They finally have ComSol installed this morning. That's great. Awesome. Um, I didn't think they didn't, so I prepared another lecture. So, well, they just emailed me this morning about it. So, but that's good for us, so we can start using it. So what I'll do, I'll give the lecture I was going to give today, and then Tuesday we'll do our introduction to ComSol. But it's good to see it's there now. Great. Okay. So. Okay. Okay, so there's a couple of things for today. So today is going to be compact modeling using MATLAB. And so we're going to do some stuff in Sugar, and I'll show you how to do it in MATLAB. Also, I made a little mistake when we started combining stiffnesses. I forgot to take into account the length. That does make a difference, so I'll make that correction today and show you guys how to do it the right way. Okay, so again, here's a typical MEMS device, and what we're going to look at is a stiffness of this folded flexure. Okay, and this is a common type of flexure in MEMS. And remember, the direction of this structure right here, this sort of like bone structure, goes back and forth this direction. So you may be wondering, like, why do you need flexures that go off like this, and why do you need 4 of them? Well, before I answer that, does anyone have an idea of why, like, what is the benefit of having a flexure like this instead of like a single cantilever beam, or maybe double cantilever beams? What kind of stability? Yeah, that's one thing, yeah. So what he said is stability. So you want it to go in this X direction, right? You don't want it to rotate, sit around this point. You don't want it to rotate. So by having these beams go off like this, that sort of resists rotation of the structure around that direction, okay? Also, it doesn't want to go in the Y direction either, right? Because if this piece right here is trying to go in this direction, well, that's attached to this, which is anchored right here. So that's another reason. So anything else? There's another reason too. So the bars don't. Oh yeah. Actually, that is a good reason. It's not the one I was thinking of, but it's an additional one. Yeah, it's good. Yeah. So, okay. So basically, what I think she's saying is, by having additional flexures here, you can get a pretty large deflection without having just one flexure bend really far. You have 2 flexures, so they only have to bend half as much, but you're adding them together, so you get twice the deflection. Yeah, so that's good. Thank you for that. Anything else? Okay, so I'll tell you this other reason, and the other reason is this. This is typically what happens when beams bend. Actually, do I have that? I think I have a, I'll have to draw this. I think I have a better, yeah, right here. Okay, I can show you right here. So here's the original beam before it's bent. It's straight like this, right? And then a force is applied on it, vertically acting downward. And then this whole structure right here bends down, and then you're in this shape. Now look at this. If you look at the projected length, it goes from here, the base, to right here. But if you were like to cast a shadow of this structure, where the light was right here and you're shining it this direction, it would appear like if you projected the shadow of this on some paper, it would appear that the length shortened. See that? See, first it went all the way to here. Now there's some little beam shortening right here. The overall length of the beam is really the same. Like if you did an integral of the arc length, it would equal this right here. But however, since you're bending the beam, the projected beam length is shortened. Okay? So how does that relate to the photoflexure? Well, here's what happens. So here's the anchor of the photoflexure, right? You have two beams going up. It's attached to a piece that you can approximate as being rigid. And then you have this other piece going down like this, another flexure going down right here. And then it's attached to another rigid structure right here. And this whole mass right here is going this direction. So as this goes this direction, what happens is that these beams, they form sort of like an S shape, like this. Okay, and these beams right here, these will move this direction. And so what happens, well, these are attached right here. So this whole beam right here, this beam actually goes from here to here. It takes these along with it. And then these bend out too. So what you get is something, maybe I should use, I should have used two different colors. But what you get is something that looks like this. Let's move this down to here. Okay, and then this piece moves over too, so we'll sort of like extend it over here, and then reduce that right there. And then so what these beams do is that they sort of take on this shape right here. Okay, and also this, because of beam shortening, remember the arc length of this has to equal the length of that. So this will actually come down a little bit to meet these guys. So it sort of looks like this when all is said and done. Like that. Okay? So it's a little shorter, projected wise. So, but even though this piece right here went from here down to here, there was some deflection right here. This piece did not deflect in the y direction at all. It only stays in the x direction, that's it. Now, again, this piece may go up and down like this as this is going back and forth, but this is pretty steady, okay? So it resists a tendency to rotate, and like someone said, you get a larger deflection because not only are you able to deflect this amount, but you're able to deflect this additional amount too. So you get twice the deflection, but only half of the deflection of the beam, and you're able to get that straight. So this structure is called the folded flexure, and it's pretty popular in MIMS because of that. Now, if, for example, if I just had something like this, let's say here's the anchor, that was the anchor here, and I just had two beams, right, and it was attached to a mast, and these beams had went side to side like this, what would happen is that the block that's attached to this would actually have a try to draw I'm trying to superimpose these things onto each other. It would not only have a component going in the x direction, but it also have a component of energy going into the y direction too. So as this swung back and forth like that, it would be going up and down as it's like, swinging back and forth. And so if you want to avoid that, use photo flexure. It's a little more complicated, but well worth it. And the reason why you don't want it to move in x direction at all is not just because it makes your analysis as, for example, a sensor much better, but it also does this. Remember, you have these comb drives right here, right? And remember how those fingers worked? You have these fingers, and they're changing capacitance. And so as these fingers deflect in and out, you're able to sense its position. You're able to sense its velocity by detecting the change in capacitance, okay? But what you don't want to happen is like, here's like one finger in two. You don't want that this vertical deflection. And that's what you would get if you didn't try to constrain that y direction. You only want to go in the x direction, right? Not in the x and the y direction. And in fact, if it goes too far in the y direction, it'll touch, and then you can short out your device. So you want to do that. So you want to keep these collinear, okay? You don't want any lateral deflection from these comb drives. Okay, so that's the reason for this. Now there are two here. So whatever stiffness is here, you're going to double it, whatever stiffness this is right here. Okay, but what I need to correct is a little mistake I did last time in explaining what is a stiffness. So, and I'll describe my mistake and how to what it's really supposed to be. Okay, so the mistake I made was that, I said, well, if you apply a force right here, you get some deflection, and the ratio of the force per deflection is this stiffness right here, and it's the Young's modulus times the layer thickness, which is out of plane, the width, which is right here across that flexure, and then the length of it, okay? But I changed the picture around a little bit, okay? And I wanted to make the difference between this flexure and this flexure. So this flexure is twice as long, so that's why for the length here, I said that this length is 2L1. So if this is L1 from here to here, this right here is 2L1, okay? And the reason that even though all of these have like 2L1 length, you want to work with this one. And the reason why is because it's that S shape, okay? So let me explain that. Okay, so here's that flexure. Okay, so this length right here is L1. And if I apply a force here, it'll bend down like this. I'll just make it the same length just to, but you guys know that there's some shortening, a little bit of shortening going on here. Okay? And remember, what we're trying to do is, for these folded flexures right here, they form S shapes. So the S shape looks like this. Like that. And so you could think of it as two beams coming together. One beam right here that bent down, and another beam right here, and you apply a force right here, and then that beam, bends up. Okay? And if you just glue those together right here, you get this beam. Right there. Okay? These forces are equal and opposite. So the forces balance out. So that's fine. So this is the shape we're trying to get. And what I'm trying to say is K1 is the stiffness of this beam right here. This is K1. This is also K1. Okay? Now, this structure right here is attached to that rigid piece on the end, but I just want to do one instead of doing both right here just yet. I want to concentrate on just one. These are supposed to be like rollers. So think of this piece right here just being able to roll vertically in the Y direction. So what happens is that this bends in an S shape and it meets that. So that's what we have right here, for example, where you have this roller. So this is able to go back and forth like that. Okay, so if that's K1, and then this stiffness right here is also K1. So the question is if you attach a force here and you bend this down, what stiffness does your force see out of that? So just remind everybody what Hooke's law is force equals Kx. So the force just is proportional by the stiffness to whatever displacement you're traveling. And so from going from here to here is your displacement x from here all the way down to here. Okay, so the force that's seen here is going to be, so let's call that K2. K2 is the entire stiffness that it sees all together. Well, K2 is going to be 1/2 of K1. Do you guys see that? How K2 is half of K1? Does anyone not see that? I'll try to explain it a little better. Well, one way you can see it is K1 alone only gets you half of the deflection, to here. But you attach another one here, so applying the same force, you get twice the deflection. Or think of it this way as a coil spring, something you guys probably all played with, like a slinky or something. If you have one coil right here, right, that has some K1, and you apply a weight here, it's going to deflect, from here maybe down to here. But if you instead have the same coil attached again, right here, and attach the same mass on that, what's going to happen is you'll deflect twice as much because of it. So here, this is K1, and that's K1. Okay? For like people in electrical engineering, think of adding stiffnesses as resistors in parallel and series, right? So if you have like a resistor in series versus having a resistor in parallel, they add differently. So that's very similar to having stiffnesses in parallel and series. Okay? So the entire stiffness here, K2, is equal to 1/2 of K1. Now, so that's just this piece right here. Okay? Now, if I add this second piece onto there, so basically this one right here is this one. I'm going to add a second one on here. Now we have two. Both of these are going to go into the S shape. Okay? But now they're adding constructively. Right? So what I have here is I have this one, plus I have another one. Right? So when I apply a force here, so remember, this one right here was K2. This whole thing is K2. Because they had a K1, and they add, well, they add sort of like resistors in parallel, and so you get 1/2 K1. But we're going to call that K2. Here's another K2. So if you look at the entire stiffness, let's call it K3. What do you think K3 is going to be? Exactly, 2K2. Exactly. And the reason why is because they're sort of operating independently from each other, right? It's not like, this is stretching and then this takes over from that stretch and stretches a little more. That's like having two springs like this, right? I have two springs. Attached to something, that mass. So it's not only experiencing the stiffness of this spring, but it's also experiencing the stiffness of that one. Okay, so this is going to deflect, very little compared to over here. So this right here is 2 of the K2, which is really, in terms of K1, you have 2 times 1/2 of the K1. So that's really just K1. Like someone said. Which is kind of weird because you're thinking like, this whole thing is no different than what this would experience just right here for half of that. So this stiffness is just K1, and the stiffness of all these together is still K1 when you combine it together. Okay? Hey, let me do that. Okay, so the next thing, is this right here. So in this one, the difference between this and this is that I got rid of this. So this is no longer constrained. This is free. And instead of applying the force here, I'm applying the force here. So let's look at that to see how that's going to bend. Okay, so this one is like this, where you have this S shape right here. Here's some rigid piece. Then you have another S shape right here. And here's where you applied your force. Okay? So remember, all of this was K2. All of this is also K2. So in this case, let's call this, let's call it K4. So what do you think K4 is going to be? Do you see how it's different from this, right? These are working together. This right here is like these two springs working together right here. This is like this spring is causing this to bend down part way, and then, initially it's like straight, and then once it's here, this is, bending down even more, right? So you're getting like twice the deflection. So twice the deflection is like half the stiffness. So this is going to be half K2, which is really 1/4 K1. Remember, K1 is just this piece right here. That first little piece right alone is K1. Okay? Now what about this? The change here is that this piece right here is now this piece, which is anchored. And instead of just having this U shape right here, I have both sides coming back and attached to this piece. So that's our folded flexure. Okay, so so in that particular case, we have something that's anchored right here. These go down like that. I'm showing the deflected shape. Trying to make this long enough. And these other pieces sort of like move down like this. Okay, so that's how that looks once it deflects. Okay, so remember, each one of these is K2. That's K2, that's K2, that's K2, right? These two right here combine together to make 2 K2. And so what happens with these right here? These combine together to make another 2K2, right? So if I were to like do some kind of way like this, so these two right here combine together to make another 2K2. However, look at how this K2 and this K2 are operating together. They're sort of operating like this. So how are these going to add together, like for the whole thing? Or just let me do it this way. It might make it easier. Instead of calling it 2K2, let's call it, so we called it K3. So this is K3. All this together is K3, and all that together is K3, to make it easy. So this piece is K3, and these two on the ends, them together, that together contributes to K3. So I got K4. So K5 here is going to be 1/2 K3. You guys agree with that? 1/2 K3? And it sort of makes sense, right? Because let's say these two in the middle moved, but these did not yet. Okay, so you have the initial deflection just due to this right here. And then we freed these up to move, and then they move additional. So you're getting twice the deflection for the same force. That means half the stiffness in order to do that. And of course, you could plug K3 back in here to figure out what it is. K3 was, remember, that's K1. Sorry, let me turn this off. Sorry about that. And then for the last thing that we have to worry about is having two, double-sided, just like that one. Okay? So if one folded flexure is K1, what's a double-sided folded flexure? Huh? 2K1. That's right. So that double flexure over there is 2K1. Think about that. It's not intuitive, right? If you apply a force here, the kind of stiffness it feels is like if you just had one flexure that was just this long. And that's it. Half of that. Because remember, this is K1. Okay? So it seems a lot of work just to get that. But again, the benefits sort of outweigh the all the complexity that you have to get to in order to achieve that. But that's an example of how stiffnesses play together. They add just like resistors. Okay. So sorry for those of you who don't know about the EE resistors, I remember how they work together. So resistors in series add like this. It's effectively like 2R. And resistors in parallel add like this, so it's effectively 1/2 R. Okay, but that's series and parallel for resistors. Series and parallel for stiffnesses, that is, they don't look like that, right? So it's not like you could take these little squiggly symbols and say, oh, well, that's just like a spring and that's like a spring. Because series resistors look like this. Series capacitors, series stiffnesses look like this. It looks like they're in parallel, right? If you look at that. But they're in series. Okay? They're adding in series. That's why this ended up being twice of these stiffnesses. This is like the parallel here. It looks like series for a resistor, but it adds like parallel. Okay? So whatever kind of method can help you remember which way it goes, use it. If you can't, just draw some simple symbols or simple diagrams to remind you how it goes. This clearly is more stiff than this. I mean, same number of springs, but if you look at that, you could just imagine that this is going to be harder to stretch than this one right here. This is going to give a whole lot more. And that can help you determine how to remember how they add. Okay, so the next thing I want to remind you guys is so we talked about this right here. So this was Sugar Cube, and remember this was a software tool that I programmed, and we're going to do some of this today. I mean, we're not going to design all this. I'm just going to get you guys started. And I'm going to give you guys the code. It's all in MATLAB, okay? So you guys can play around with it yourself. But I know this is hard to see, but I'll show you guys how to work a couple of elements like the beam and the anchor, okay? And we'll do it straight from MATLAB. You don't have to use this GUI right here, because if you guys could do it straight from MATLAB, then you guys can modify it, right? And make your own wrappers around it and play around with it and use it for other things, which is, quite more useful to some people. Other people just like this part. You just tweak things. I want to show you. Oh, okay. So, for example, I was trying to find a picture that had one sweep. Okay, so basically, here are a few parameters right here, and those parameters. Here's the width of the appendage. The next one right here is the length of the appendage from here to here, and this one right here is the voltage that's being applied across that appendage, okay? So, but as you can see, it's a sweep. I'm sweeping from 0 volts to 40 volts, and here are the number of data points, and it's 5. So here goes 0, here's 40, and there's 5 points along here. And so what happens is that when I'm at 0, the flexure is just straight like this. Then I'm applying a voltage, and I'm stepping it up in terms of from 0 to 40, and then this thing starts bending down like that for every time. And so what you have here is this is the height off the ground that the little microid lifts off the ground as the legs start bending, and it goes up like that. Okay? So that's what's happening here. And so you're just plotting height as a function of voltage. It is negative, that's why it's going down, but and in the net list, which I'm going to show you guys today, let me see if I got large that so you guys can see. Yeah, the resolution's pretty bad. Yeah, a little better. Little. Okay, so Oh. Yeah, where is it? There should be. Oh wait, I'm sorry. Okay, this is going to be not a really good example because, yeah, because it's not showing you the parameters. But basically, I'm going to show you guys how to do this today with the beam and the anchor. But here are the parameters that would show on the screen, like right here. Those are the things that show right here. And so you can choose which ones pop up, right? And then it shows all the sliders. Because you're trying to make something that's useful for you or someone else to tweak the design a little bit. Okay, so these are the parameters that would show. And it's the segment length, L, phi, the honeycomb angle, number of rows, and number of columns. So 4 parameters would show up, and then what you can do is define what is the initial value, what is the final value, and how it's sweeping. Okay? So this is how to do that. You can change it. If you don't want length, phi, rows, and columns to show up, maybe you would want to do the width. Maybe you want to change the width of that, have that be a parameter. If you do, you could just add it here, or you could, in fact, I could show you. Yeah, so on the video, if you remember, there's this piece on the video, and I don't think we got to that part yet. Where was that? Here it goes. Okay. Oh, and then back up a little bit. Okay, so on this structure right here, I have some parameters that's already shown right there. But I'm going to open this up so you can see the net list, and then you'll see how I add a new parameter. Gap doesn't exist. Gap is this space right here. But let's say I want to parameterize that to see how it behaves. So I'm typing in the word gap. Typing it in, and I'm putting some initial values or whatever like that. And then when I go back out, you'll see the gap parameter there. Okay? So see, this did not previously exist. Now it's there. Now it's something that you can play around with. And you can go from this value to that value and sweep it. So this right here is it being swept out. This is what I'm doing modal analysis on the same structure. Oh, see, now the gap is larger now. See that? That's the phase. The one before was the frequency, like the Bode plot. And I could take slices too. Here are slices of it, and I could do different degrees of freedom as well. These are like how it would resonate at different frequencies. Okay, and these are the mode shapes. This is what the mode shapes look like if you want to look at those kind of things too. Okay. Okay, but okay. Anyway, that's that. Okay, so one thing I want to talk about before I get to MATLAB is this structure. So this is like a publication I made many years ago. Yeah, so a long time ago. But basically, I'm trying to describe, how I created this mirror in the software. So first I described how the mirror has components. It has this moment arm. It has the comb drives and tethers. This disc right here. And so you have to make compact models of it. And this is kind of weird too because this mirror right here is a plate of silicon, but as you can see, is recessed. So this part right here is dug out. So the reason they wanted to do that, I didn't design the mirror. A colleague of mine did, and I just modeled it in the software. But they designed this, and they said that the reason that they needed to have it dug out is to reduce its mass, so it could have a certain frequency. So that's what they did. They reduced the mass so it could have a higher frequency. um, all these components. And so you try to model that kind of thing using compact models. If you try to do it using something like FEA, you need a lot of memory. And it'll still take you a while with today's processors, even though they're pretty fast today. It's just a lot of computation involved. And it's kind of difficult because look at this. It has these perforated beams right here. You see that? It's not an easy thing to really try to make a compact model for. They could design it a little more easier, but a little more simply, but they didn't. So here's my compact models that I'm creating. So I made a model for this, and here are the parameters. Here's a compact model, the parameters. It has nodes A and B. Here's node A, here's node B. Here's what these parameters mean. The R radius, width, H and H2 correspond to this. The moment arm looks like this. Of course, the real one is a little longer, but it's parameterizable, so you can change the length of it. So, but here are the parameters around. So you could tweak the parameters and change that mirror design into something totally different. Here's the perforated beam, right? And really, so this right here is a cantilever. That's a cantilever. That's a cantilever. These are like all cantilevers that I'm just piecing together, and I'm calling it one piece, and it's called moment arm lever. Here's a whole bunch of other cantilevers too, but they're pieced together in a way that they make sort of this ladder type of structure. Okay? That's just a regular cantilever beam. And here's a voltage source right there. Here's a comb drive right here. Their comb drives are also perforated, okay? But I made a lumped compact element just called a perforated comb drive. And what you can do is you can go in there and choose your number of fingers, and it would generate this structure. Right here it has 5 fingers, but if you wanted 20, 100 fingers, it would just make it longer with 100 fingers, okay? So remember, for these comb drives, the number of fingers creates greater force if you increase your fingers, even if you're applying the same voltage, which is really nice. But of course, it takes more space. And here's an S-shaped beam. Oh, I should explain this. This is very subtle. On this structure right here, oh, you guys, yeah, this flexure that's holding up the structure, it looks straight, but it's not. It's an S shape that is pre-bent, and they did that on purpose to try to keep the comb fingers from getting, messed up, because they're not using a folded flexure, right? So they did that reason. So this is what it looks like in the software in MATLAB. So here's the mirror, right? This is a top view looking down. Here's the perforated beam. Here are the comb fingers right here. It only shows one set of the comb fingers. It doesn't show the engaging set. Typically, the part that moves is called the rotor, and the part that doesn't move is called the stator. So stator, rotor, even though it may not be rotating, okay? But that's what they call it. And so if you want to model the stator, you can, but it doesn't add anything to the dynamics because it just stays there and never moves. So if you're going to say, well, I know what the force on these fingers are going to be, so I'm just going to model that's the part that's moving. And then for the stators, I just don't have to show those and save myself some computational time. Here are the cosine-shaped beams. It's a very long, wide wavelength type of thing here. So this thing moves back and forth. And as it moves back and forth, it tugs on these moment arms, and it rotates this mirror about these beams right here. And the reason the beams are perforated is in order to get like a decreased rotational stiffness. Okay? If they were solid, it'll be harder to torque, right? So for a certain amount of voltage you apply here, it pulls this and it rotates the mirror. And the reason that they were doing this is they were trying to make this thing called smart dust. And what smart dust are these little tiny motes that they can place around, and they can communicate with each other through line of sight. And so they would shine a laser beam on these things, and they would be able to steer where that laser beam would hit and communicate with another dust mote. So that was the purpose of that. Yeah, because if you just do it with radio goes everywhere, right? So there's lots of wasted energy. But if you could like steer, line of sight beam, that is more efficient. So this is what the net list looks like. What I mean is that this entire structure is represented by this net list. And this net list is like Legos, but you're typing out how the Legos are pieced together. Okay? Like, for example, see this moment arm lever right here, B0, B1, B2. Node B0, node B1, and node B2 are right here. So that's what this element is, called moment arm lever. It's attached to something called the perforated arm that goes from node B2 to B3, B2 to B3. And then that is attached to something called this perforated beam that goes from B3 to B4. From B3 to B4, this is one element, but it creates all these other things in there. And then at B4, it's anchored down. Here's an anchor that's attached to the substrate, and that's the B4. So you can see how you can piece these things together. I have all the parameters right here. I removed the numbers just because otherwise it would be like really long. But all the numerical values have been removed, but the parameter names are still there. And so by just going through, like, all the nodes are labeled, and you can go through this and see, how these things are created. Like C4 right here, that's, I did an array. So right here it says for j equals 1 to the number of drives, I have it go through a loop. So the number of drives has, quite a few drives, like, just 4. Okay, so it has 4 drives, and so basically, every time it goes through, it creates this. It goes from, so it goes from 1 to, I guess, 4. So it goes from C1 to C1 plus 1, so C2. The next one goes from C2 to C3. Next one goes from C3 to C4, right? And then C4 to C5, right? And so that's how that keeps going. So you can do arrays with the nodes. And that's why these nodes right here are in parentheses. So they're not the same node. That's C1, C2, C3, C4. Yeah, but that's how the whole structure is put together. And it was really cool because they were working on this for a very long time, well over a year. And I think it was 2 years, in fact. And they were trying to determine how to optimize it. And, oh yeah, here's like a 3D. Oh, see, it is recessed for the model as well. Here's that moment arm. Oh, here's that perforated beam, how it rotates. I'm comparing it to FEA right there. That's COMSOL. Yeah, so that's the thing. If you're making a compact model, one way to verify it is to compare it with FEA. So, okay, so let me explain. There's a difference between verification and validation. So verification is like taking the method that you're doing and comparing it to some other kind of method that is completely different than yours. And if you get the same answer, that is called verification. Validation is when you compare your method to a true experiment. Okay? Totally different things, but they're very important concepts. So whenever you do modeling, you're like wondering how do you, how well can you trust that number, that result you're getting? And what you do, you validate it. I mean, well, yeah, you can validate it in an experiment, but sometimes it's you don't have the funding for that. But you can verify it by using a different method to see if you get about the same kind of answer. And that's that sanity checking that you want to do to make sure that you're on the right track. Because sometimes you get really interesting results, and you're like, wow, that's amazing. Is that really, what I got out of that? Is that, something new? Um, so this is the end result right here. And as I was showing you guys last time, you could find out what parameters give you the best angle, the best tilt angle, for this, whatever voltage you're applying. What should the moment arm length be, and what should the perforated beam width be in order to get like the best angle? And that's something that's not intuitive. I mean, you can't look at the structure like, oh, I know what to do. You have to put a model in and tweak the parameters and plot it out to see what it looks like. Okay, so now let's try MATLAB. Okay, so remember, this is code that I'm going to give you guys. Can you guys see that code? Like, what I typically do for MATLAB, I know it's probably a while since you guys have used MATLAB. Has anyone never used MATLAB? Just, a few people. Okay, it's not that bad. Especially for what we're doing. Okay, but let me ask this question. Do you guys know any code? No? No. Again, it's not that bad. Okay, so in order to use sugar, the name of the tools, the name of the code is called sugar. In order to use sugar, there's only a few keywords you need to know, okay? And you don't need to know all of MATLAB to use it. You just need to know some keywords, which I'll show you guys how to do. Okay, and I'll put the keywords online. Okay, so basically, let me show you guys how this. So typically, here goes a simple example right here. Okay, so this is a file, and so the way MATLAB works is that, and this is really an old version of MATLAB. Is that text too small for you guys? Can you guys see that in the back?
Could you zoom in just a little bit?
Okay. Yeah, is that possible? Let me go to, is there a view here? Huh. Do you see something on there where it allows me to do that? Huh? Okay.
Yeah, so in display settings, in Windows, under scale and layout, change the size of text option. Let's type in display and we'll on one.
So you're saying do what?
Type here to search, Windows.
Right here, display settings?
Yeah, or that, there you go. Scale and layout.
Here's 300. Is that better? In the back? Okay, great. That's good. Thank you for that. Okay, so now this is not MATLAB code. Okay, this is a text file, and what it is sugar code. So sugar code is just some code that I made up, and that's all it is. I could have used different kind of syntax or whatever, but the syntax I'm kind of following is that of SPICE. And for those of you who are not EE people, SPICE is simulation program with integrated circuit emphasis. I think that's what it means. But basically, it was something that was created back in the 70s, and it was offered for free. And now just about every software tool that models circuits has spice in it somewhere as its DNA. So they have a format like this, and they called it a netlist, where they had some kind of model, then they had some parameters, how it's connected, like from node A to node B. Then they had the parameters, the length, the width, the height, and well, I'm using angle. For in Spice, those parameters were for electrical elements, like resistance, capacitance, things like that. But I have to put in geometry for here, right? But it's the same kind of thing. So it's just something I made up. What you have here, here's a file that it uses, and this includes the material properties. This file is called mumps.net. It's not a disease. It's not a virus. Mumps. It stands for multi-user MEMS process. Okay. And in there, I just have the material parameters of like silicon, polysilicon, gap spacing, things like that the software needs to use in order to get the deflections and things right. Here's an anchor. So you saw what an anchor was, and it's just something that attaches whatever structure you're making to the substrate. Here's a beam right here, and it goes from node A, where that anchor was, and here's the geometry of the beam. Okay, there's no spaces, as you can see. U stands for micron. Everything's in standard international units. Okay, this right here, that is in radians, but you can put it in degrees, and I'll show you how to do that, because like some people don't like thinking in radians. They think more comfortable about degrees. And this is some kind of force that I'm applying at node B. So if I were to draw this, and I'll show you guys how to plot that out. I mean, how to show it in MATLAB. And remember, the code I'm telling you about today is all you need for MATLAB. You don't need to know everything about other things about MATLAB, to run Sugar. So even those of you who don't code. Okay, so it has an anchor that is at node A. Okay, and I should say this too. So let me talk about angle first. So X, Y, and Z. So X, Y, and Z is like this. Wait a minute. Okay, X, Y. X, Y, and Z. Okay. So your index finger is X, your finger next to it is Y, and your thumb is Z. Okay? So I always think about that's like the right hand rule, I believe. Okay? X, Y, Z. Okay? Now, every object in Sugar is born living on the X-axis. So if I were going to have a beam, it is born there where the first node is A, second node is B. Or the first node could be Jason, and last name could be Clark. It could be, it's just your node names, but it's born there. Then what you do is you send it through a series of rotations. Here, you're just rotating about Z, amount pi. So that's 180 degrees. So then what happens is born there, then you rotate it 180 degrees, or you rotate it pi, and now it's now sliding this direction over here. Okay? That's what that means. So your first structure is like this. It's really short. Here's node A, but it's stubby, but it has rotated that direction. This other structure right here is a beam that goes from node A to node B. Oh, I should also say this. There are no coordinates in here. No coordinates. Everything is relative. Okay? So the first node I coded it so I know where it is. The first node is at 0, 0, 0. Okay? And then the next ones are just, other coordinates after that. But you don't need to worry about coordinates. Just think about how things are connected together. And so it goes from node A to node B, has a length of 100 microns, width of 2 microns, layer thickness of 2 microns, and it rotates about Z0. So it looks sort of like this. So, I think it is 10, not, yeah, so it's a little bigger. So it looks like that, where the length is 100 microns. And then now I apply a force at node B, and that force is 10 micronewtons. And the angle of that force is pi over 2. So remember, even vectors, force vectors, they are born on the y-axis, on the x-axis, and then it's rotated up pi over 2. So it's like this, and it's attached right here. So there's a force that goes up like that of 10 micronewtons. And so that's a very simple structure, okay? And so let's try that out. Okay, so in Sugar you do this. You save that, and it's called test 3 here. And I typed on here what this is. And I'm gonna put this on Canvas for you guys so you guys can try it out. But basically, let me type in the rest of the things. So here's my functions I've made, my M files. I have something that's called CHO load. CHO, that's shorthand for sugar, carbon, hydrogen, oxygen. So I just didn't want to type 5 letters, I wanted to type 3. For some reason, I thought it was going to save me lots of time. So CHO load. So it takes this file called test3, and it loads it up, and it creates a data structure. You don't have to worry about it. That goes inside that's happening inside the code. But it's called net. So net is a data structure that represents this. After you have net, then you want it to run some analysis. So you say Q equals CHO DC. That's like DC analysis. It's like static analysis. And then of net. So you put this variable into this argument right here, and the CHO DC runs that, and it outputs a vector Q. Q is like the displacements of all these, of everything here. So I should say every single node in the software has these coordinates. Okay, of course, it has X, Y, and Z, but it also has rotation about the X, rotation about Y, and rotation about Z. So you can figure out, if I lift it up like that, how much does that beam actually rotate a little bit? Okay? So you could do that. And then once you have this, then you want to display it. So then you could say CHO display. It needs 2 parameters. It needs net, because it needs to know what you're talking about. And it needs the deflections, which is Q. Okay? So that's what I'm going to do. Those are all comments. So in MATLAB, you use these parentheses to make comments. So when you run it, it ignores all this stuff. But I put this in here to remind you guys how to run it. Okay, so I'm just going to copy and paste this onto the workspace. So you go to the workspace and you run that. And then here's what net is. If you don't have a semicolon after that, like I put a semicolon, it doesn't show it. If I take the semicolon off, then it shows you what that data structure is. It has all this stuff in it right here. Then for the next thing, I'm going to copy and paste what this is, CHO DC net, like that. And that just loads what Q is. Okay, I can take the semicolon off, and this is what Q looks like. Here's X, here's Y, and Z. Okay, next, I'm going to do CHO display. Just copy and paste it in, and then it should display something. Yeah, here it goes right here. So as you can see here, here's that structure. There is a force there's a force right here at that node that's pointing up this direction of 10 micronewtons, right? And here's the anchor, here's that beam, and it got deflected up. So that's like that's a cantilever. Now you know how to do cantilevers. But the cool thing about it is that you could attach other things. Like remember, like on that, on this example right here. Now granted, since I made the code, I know how to do all this stuff right here because I have all this experience, right? But I'm just showing you guys that all the stuff right here was made of cantilevers. Lots of cantilevers, but you can make all kinds of structures with cantilevers. Even structures that sort of like aren't exactly cantilevers, you can approximate them as cantilevers even, right? So there's a lot you can do, and that's an example of what you can do once you get like a little more used to everything. And in my last minute that I have with you guys, what else can I say? Oh, okay, so let's try this. Let's go back up to here. Oh, I'm just going to put all this in one line because why type everything individually when you could just type it all together? Okay, so that's what I'll do. So when I go, I'll save it and I'll go over to here and it's all one line now. Okay. Now what I'll do, let's add some things to it. Like let's say, copy and paste that, and let's say I want to go from node B to node, I don't know, let's call it B2. And then let's make the angle 45 degrees. Oh, so yeah, so for degree you go degree, and then put in parentheses 45. Okay? So then let's run that. And see? The force is still here, but I have this extra piece here. I can go in and I can play around. I could change the width to twice as much. So I can say that times 2, right? And then I can go and then run that. And then, as you can see, it's now wider. And because it's wider, it doesn't bend as much with the same force anymore, which makes sense, right? And you can like look at it from different angles to see what that looks like. What else can I do real quickly? Yeah, okay, well that's all I can have time to show you today. And that's just to get you guys started. So again, I'll put the sugar code online and I'll give some instructions for people who've never ran MATLAB, step by step of how to get this going, get it up and running. And you can try, just play around for yourself. Because it has lots of potential. And you can do lots of things with it to just try different things. And it's something that you can, make your own by adding things to it. Okay? So that's it for today. See you guys on next Tuesday.